Log on, tune in, find out. Another good idea from Cambridge.
This talk is by Alessia Mandini from Lisbon, and she's talking on hyperpolygons and moduli space of parabolic Higgs bundles.
Thanks very much to the organizer for the very nice opportunity to be here. And the results that I will talk about today are in joint work with Leonor Godinho. And the main result that I want to present is the existence of an isomorphism between an hyperkähler manifold, the so-called hyperpolygon space, and some moduli space of parabolic Higgs bundles over CP1 with this assumption that I made here. I want them to be rank 2, holomorphically trivial, and to have fixed determinant and trace-free Higgs field. In particular, we will see that this isomorphism restricted to an isomorphism at the level of polygon spaces and at the level of ordinary parabolic bundles. And then as an application of this result, I plan to describe the wall-crossing behavior of the hyperpolygon space X alpha. Actually, this was our original problem that we wanted to investigate when Hausel suggested us that such a relation with moduli space of parabolic Higgs bundle might have existed. So this took myself and Leonor through a big journey through parabolic Higgs bundles to understand in the end that Thaddeus has solved the problem that we were considering for in his paper on variation of moduli of parabolic Higgs bundle. He has in fact solved it in bigger generality, but in particular also for our space H beta. So we also worked out another application. In fact, using the geometry of hyperpolygon spaces, we can compute intersection numbers and cohomology of some special components, and via our isomorphism we can import them on the side of parabolic Higgs bundles, but I won't speak of this last part during this talk. I'm of course happy to talk about it later if anybody is interested. So I will start the talk by describing the spaces, the spaces that are on the right side of the diagram, polygons and hyperpolygons. So the polygon space is a Kähler manifold that can be described as a symplectic reduction starting from the product of n spheres of I'm sorry, the colors are really not good. I'm really sorry about that. So you construct such a manifold starting from the product of n spheres in R3 of radius alpha I, and then this is a symplectic Kähler manifold where the group SO3 acts by rotation on each of the spheres. Then the moment map for this action takes n vectors v1 through vn to their sum as vectors in R3, and then so the polygon space is then defined to be the symplectic quotient of the product of spheres by the diagonal action of SO3 at the zero level set. In particular, I mean, it's called polygon space precisely because a n-tuple of vectors v1, vn lies on the zero level set for this momentum map whenever the closed path that we can construct by applying the vectors v1, v2, one after the other, whenever such paths close. So this is what we call a polygon in R3, and we are considering moduli spaces of such closed configuration, modulo rotations and translations. When smooth, the polygon space M alpha is a Kähler manifold of dimension 2n minus 3. So I want to start with some examples. The first that I wish to give. Right? Yeah. So consider the length vector to be 5, 1, 1, 1. Then we have a very long edge of length 1, and there is no chance to close such a path with the remaining, so this moduli space is empty. Of course, we have less trivial examples. We can take the equilateral polygon space. This is clearly not empty because, for example, we have the square in such a space, but also we have a more degenerate configuration like this one lying on a line. Then this lined polygon as an S1, the isotropy is the S1 of rotations around the axis that it defines, and this produces singularity when we go past the quotient. This is so to motivate the following statement that the polygon space M alpha has a singularity if and only if there exists an index set such that this scalar quantity vanish, where this scalar quantity is just the sum of the length alpha I for I in our index set minus the remaining length. In this example, for example, just take S to be 1, 2. Then, since this scalar quantity will play a crucial role in the study of polygon spaces, let me call it epsilon I of alpha. And we say that alpha is generic when this scalar quantity never vanishes. And some more notation, in an index set I is short whenever the epsilon I is negative. So, with this example in mind, let's give a broader description of such polygon spaces. They are the Kähler quiver variety associated to the star-shaped quiver that I've in this figure, when we have n outer vertices and a central vertex 0, and then the edge set assigns an arrow from any of the outer vertices to the central one. And if we choose representation spaces to be C for the outer vertices, and C2 for the central one, then the representation space of such a quiver give us a homomorphism from C to C to C2 whenever we have an arrow. So the representation space is C2n, and we obtain the associated Kähler variety by performing reduction on the representation space.
Or the length of one.
Or the
length of such a
I'm not attaching length here.
I mean the number of vertices in each length.
We have n edges, and then it's very better. And then the length alpha comes here.
No. I mean the number of vertices in each edge.
It's one. Yeah. Yes. Of course, this is just a brief remark. If you have more, that would correspond to having conjoint orbits of SUN. This is just SU2. Yeah. So anyway, then we perform the reduction as in here, and the polygon space is the reduction of C2n by the group K at the level set 0 alpha. So this is, I think, a nice way to move to hyperpolygons, which are the hyperkähler analog of such polygon spaces. And a thing that I want to remark is that they are called hyperpolygons just because the construction is the hyperkähler analog to polygons. But there is, as we will see, we lose a lot of the geometric intuition that we have for polygons. So we construct them from the very same quiver as in here. Then we start from the cotangent bundle to the representation space. The action of the group K is given by conjugation, as I've written there. And I've also written the moment map condition because I will need to comment on that later on when we talk of the isomorphism, so this slide will come back. And then the hyperpolygon space is the hyperkähler quotient of the cotangent bundle to C2n by the group K at the level set 0 alpha 0 0. Okay, so this was set. Come back. And I want to give some properties of such spaces. As I said, it's an hyperkähler manifold for every generic choice of alpha. It's non-compact and it has dimension 4n minus 3. And in particular, the polygon space sits inside these hyperpolygons as the collection of those points PQ such that the P coordinate is identically 0. Even more, the hyperpolygon space contains the cotangent bundle to the polygon space. We can rescale the length vector with no harm. And there is also a notion of stability, which is actually the notion of stability for quiver varieties that has been adapted by Conno to this special setting. and that it's given in terms of a straight set. So we say that S is straight at a point PQ if and only if the Qi coordinates are proportional whenever like that I and J are in the set. So then the point is said to be stable if Qi never vanishes, and if whenever we have a straight index set such that the P coordinates are 0 in the complement, then S is short. And then one can of course construct the corresponding moduli space as in here and prove that it is the hyperpolygon space. So as I was mentioning a moment before, we lose a bit of the intuition. What I mean is that it's nice to draw a polygon, and we cannot draw all hyperpolygons, but some of them we can. Precisely those that lie in the so-called core of X alpha. This here is a summary of the work of Radden, Proudfoot, and Conno in mixing the two. So to define the core, I need to also to speak of an S1 action on the hyperpolygon space, which is given just by multiplication on the P coordinate. And then the momentum map for this S1 action takes an hyperpolygon PQ to the sum of the squares of the PI coordinates, and then this is a Morse-Bot function, and its minimum is attained at the polygon space where all the coordinate PI are 0. And there are other critical components that Conno shows that are in one-to-one correspondence with short sets of cardinality at least 2. And such critical components have been characterized by Radden, Proudfoot as the collection of those hyperpolygons, such that both S and its complement are straight. We will see in a moment that this has some geometric meaning, and that the PI are 0 for every in S complement. Then if we let US be the closure inside the hyperpolygon space of the flow down from this critical component's excess, we have that the core is defined as the union of the minima, the polygon space, and these flow downs. And we have sort of the US components for any short set of cardinality at least 2. So this is the characterization, the nice characterization that I was mentioning before due to Radden and Proudfoot. If we have a point PQ in a component of the core, then it can be described as a pair of polygon, where we have a polygon in R3, which is this one that I've tried to draw in blue. And then we have a planar polygon that lies in the plane orthogonal to this vector W, and is attached to that to a vertex. This is the recipe to construct the edges UI for the planar polygon, VI for the spatial one, and W, which is sort of a special one. So let me spend some time commenting this picture. The first thing is that when the PI coordinates are all 0, then the UI are 0 as well, and so the planar polygon disappear. And on the other side, by the moment map condition, we have that the vector, by this moment map condition here, we have that the vectors VI have length alpha I, so they have fixed lengths, while the vectors UI, there's no reason why they should have fixed lengths. Some more example of such hyperpolygons. So, for example, the core component US intersects the polygon space in this submanifold, which is formed by those polygons that have edges VI all aligned for I in S. And let me call this, MS of alpha. It will come later, and I'd forgotten. And the other critical component, we have that an hyperpolygon is in the critical component XS if and only if the polygon in R3 is degenerate, so it's in one point. And this is precisely the condition for S being straight and S complement being straight. And then we are left with the planar one. In between, there are all configuration from here. We start increasing a bit the planar one, and this is sort of the description of the flow down in a very and waving way. So an example which I think it's of some interest is for 4 edges. In this case, for every generic choice of alpha, there are always 3 sets of cardinality 2 that are short, and so we get 3 critical points, x1, xs1, xs2, and xs3. And also the minima is either the polygon space when not empty, or when it's empty, it means that there exists a short set of cardinality 3, as we had seen at the beginning with the example 5, 1, 1, 1. In this case, we would have that the index set 2, 3, 4 is short and of cardinality 3. So the minima, so this is the union of 4 CP1s arranged like this. So let's keep polygons and hyperpolygons aside for a moment and move to parabolic Higgs bundles. This is more to fix my notation than, I'm really talking to the experts. So I will restrict my attention to rank 2 parabolic Higgs bundles over CP1. This is rank 2 precisely, as you were mentioning, because we have only 1 vertex in the quiver. And then we have a parabolic structure on a rank 2 holomorphic bundle is just the data of a weighted flag on the fiber of each of these mark points. There is a natural notion of parabolic degree and slope, and then that allows us to define stability. So a bundle E is stable if and only if the slope of any parabolic line subbundle is smaller than the slope of E, or semi-stable if equality can hold, and as usual I will denote by m beta 2d the associated moduli space. Okay, so Higgs bundles over parabolics. So here I apologize, now K is the canonical bundle. Before it was the group, but I think it will create no confusion. So a parabolic Higgs bundle Phi is a pair of a parabolic bundle and an Higgs field Phi that to me is a meromorphic endomorphism valued 1 form that has poles in our parabolic points and such that the residue of the Higgs field is nilpotent with respect to the flag. And this condition will be really crucial in proving our isomorphism. Then the notion of stability extends in the natural way, and we then construct the moduli space of beta stable rank 2 degree Z parabolic Higgs bundle over CP1, and I will put a not lambda to mean that I fix the determinant and consider trace-free Higgs field. Then we make a further restriction to the space H beta by requiring of only considering bundles that are holomorphically trivial. And this is the space that we are in fact investigating. So beta is generic whenever stability is equivalent to semi-stability, and in this case the space H beta, as the one above, is an hyperkähler manifold. So since it's such a relevant notion, let me make it, well, this will be probably the only computation that I show in the talk, but let's see what means that to have a strictly semi-stable bundle. So if E is such a bundle, it means that there exists an invariant line subbundle L in E such that the slope of the subbundle is equal to the slope of E. And since we are in rank 2, a subbundle has to be a line subbundle, so the fiber is actually just the flag is just the fiber itself. And we only have to say how we assign the parabolic weight. So we assign a weight beta 2 of x whenever the fiber intersect the flag precisely in the one-dimensional subspace, and beta 1 otherwise. So if I call SL the index set for such that the subbundle L inherits weight beta 2 at xi, I will call it this sometimes the discrete data of the subbundle. Then the parabolic degree of the subbundle L is just what's written in here, this sum, and then so the fact that the slope of L is equal to the slope of E just translates, by doing the computation, to this to the vanishing of this sum. If you look at it a moment, you recognize that this is what I've called before epsilon SL of alpha, when alpha is the difference of the parabolic weights at the same parabolic point. So I hope that this already gave a flavor of the correspondence that we will obtain. And we say that beta is generic anyway whenever epsilon s, this quantity epsilon s of beta 2 minus beta 1 doesn't vanish for any index set. This was my first attempt at it, to give you some analogies. The second one comes by talking of a natural S1 action that is defined on this moduli space of parabolic Higgs bundles, which comes just by multiplication of the Higgs field. Then the moment map for this action is a Morse-Bot function, and whose critical points have been studied in full generality by Simpson, and in the rank 2 there is a very nice paper by Boden and Yokogawa which helped us a lot. So a bundle E phi is a fixed point for such action if either the Higgs field is identically 0, and in this way we recover the moduli space of ordinary parabolic bundles, and it will be the minima for the moment map, or if the bundle E phi sits in one of these submanifold M d0s, which are labeled by an integer d0 and an index set s, where topologically the bundle splits as the sum of two parabolic line bundles. d0 is the degree of E0, and the index set S is the discrete data of the subbundle E1, as in here. Okay, so from Boden and Yokogawa one can compute that when D is 0, one has that such submanifold M d0s is not empty if and only if these two inequality hold. Now, looking at them, you can recover that you obtain short sets S of cardinality at least 2 whenever the d0 is equal to 0, as it is imposed by requiring holomorphically trivial bundles. So the fixed point set for that S1 action is M beta, which is the minima of the moment map, and then the union of these components M0s, which are again in one-to-one correspondence with short sets of index 2. Now the expert might recognize that the downwards Morse flow from these components coincides with the nilpotent cone. I've learned this in the paper by Garcia Prada, Goten, and Munoz, where they generalized to the parabolic case, a work of Hausel in the non-parabolic case. So the last example that I want to give you in order to give you an idea of the correspondence is again the case when n equal to 4. So now we have 4 mark points. As before, there are 3 index 2 critical points in this case. They are points corresponding to the 3 short set of cardinality 2. So we have these critical components M0 Si, and then the minima is either the moduli space of ordinary parabolic bundles where non-empty, or if it is empty, by again using the work of Boden and Yokogawa, you can show that there exists a short set of cardinality 3, just as before. So in this case, the nilpotent cone is the union of 4 CP1s arranged as in here. I want to stress, since I believe that there is some interest in this space. I've heard a talk here by Simpson when he was giving exactly the n equal 4 case. If you don't require the bundle to be holomorphically trivial, then you get an extra index 2 component, which is this one, corresponding either to d0 equal to 1, and then the index set is 1, 2, 3, 4, or to d0 equal to -1, and then the discrete data S is the empty set. So in dropping the assumption of the bundle being holomorphically trivial, we obtain 5 CP1s. One is the minima and the other are the flow downs. Okay, so if you want to prove an isomorphism result, as we want, and you hope for it to be S1 equivariant, you really have to assume that the bundles are holomorphically trivial. So this is the idea. This is the isomorphism that that I'm talking about. So the moduli space of parabolic Higgs bundle H beta is isomorphic to the hyperpolygon space X alpha whenever the length vector is determined as the difference of the parabolic weights. Moreover, this isomorphism is S1 equivariant with respect to the S1 action that I have introduced on hyperpolygons and on parabolic Higgs bundles, and thus restrict to isomorphism between the polygon space and the moduli space of ordinary parabolic bundles, so between the minima, between the critical components, and also between the associated flow downs. The idea of the proof, and just what I like of this result, is that we really constructed the isomorphism, and this allows us to translate results from one side to the other. So given an hyperpolygon PQ, how do you construct a parabolic Higgs bundle? Topologically, it has to be trivial, so it's just this. And the flag is given precisely by the image of the QI, which was the map in the quiver. Okay, so this is the flag structure at in the fiber of the parabolic points, and then here it where it comes back. Then the Higgs field, since we are considering bundle on CP1, the Higgs field is uniquely determined by setting its residue to be the traceless matrix QI pi. Note that this moment map condition guarantees us that the sum of the residues is 0, and hence the Higgs field is uniquely defined. So this was the isomorphism, and the application that I want to describe is the following. So what I mean by wall crossing, well, a wall is just, which I will call WS. Let WS the wall of equation epsilon s of alpha equal to 0, and then we want to study the differences from the spaces when we take alphas on either side of a wall. So the polygon spaces M alpha plus and alpha minus are birational, and this is a very general result due to, well, for such kind of spaces, not just for polygons, due to Guillemin and Sternberg in the symplectic setting and to Brion-Procesi in the more algebraic geometric setting. But what I believe that's nice for polygons is that the birational map between M alpha plus and M alpha minus is precisely the so the loci that we blow up are the submanifold MS alpha minus and MS alpha plus that we have met before as the intersection of the polygon space with the core component US. So we have vectors aligned. And also these are both the resolution of the singularities that you get when you have the singular quotient M alpha C, where you have a polygon on a line. Okay. So knowing our isomorphism, the wall crossing for parabolic bundles, the analog result had been proven by Boden and Hu, and I also believe that Thaddeus Give proves the existence of a common blow-up, I believe. So once you have this result, when we started studying hyperpolygons, and Konu proved that hyperpolygon spaces are all diffeomorphic for every generic choice of alpha. The same result for moduli space of parabolic Higgs bundles was proved by Nakajima. So the spaces in fact have the same diffeotype, but they are not the same as S1 spaces. And this is precisely what we are talking about when we speak of wall crossing. So what we did with Leonor, we adapted Thaddeus' work on moduli spaces of parabolic Higgs bundles. He proves that that H beta minus and then H beta plus have a common blow-up, where the loci along which the loci Pu minus parameterize all non-split extension of L minus that are beta minus stable but beta plus unstable, and where this L minus is a trivial parabolic line bundle with our assumption. It works in much bigger generality. And so here come myself and Leonard that just can say, oh yes, the same happens for hyperpolygon spaces. They also undergo a Mukai transformation, and when in this diagram, when you see H read X for hyperpolygons, when you see beta read alpha, then the same result holds, and when you see PU minus or PU plus, read the core component US. So as crossing, and here I'm even ahead. So this is my final slide where I will spend some time hand waving. So what happens when we cross a wall W for hyperpolygons is that we have one of the core components. Let me see if I can do it. Yes. So one of the core components, the core component US associated to the wall, disappears. The core component associated to S complement appears. And the changes in the other core components are ruled by their intersection with US and US complement. In particular, we recover the description of the wall crossing for polygon spaces that I given a moment ago. So in here I've tried it's very difficult to draw a core, but anyway, these are the core components that are relevant to the that are affected by the wall cross of the wall 1 to 5. So you can see here, this is the CP2 that disappears. It's the core component U1 to 5. And after crossing the wall, we have that another embedded CP2 appears. These are all spheres, CP1s. So another embedded CP2 appears. Embedded in another way, of course. So these lower thing, M15, N12, and M25 are the polygon spaces, are the components MS that I was talking before. Okay. So here at the level of polygon spaces, what we are doing is we blow up the point M125 to CP1, which is the component M34. So this is precisely the wall crossing for polygons that I've described. And it fits in this bigger picture as I've explained here. So this is what I wanted to say. Thank you for your attention.
Time for a very quick question, quick answer. I'll ask the question then. I asked you some time ago this, but maybe you haven't answered now. If you consider the involution in the moduli specific bundles that goes from E phi to E minus phi,
Exactly.
recover the polygons, right? But there are other fixed points normally which relate to, as in the same way as SU2 polygons to SU2. This would relate to SL2R. Are there really? You have these components?
No, I have not them ready. I think these, I mean, they might be describable as pairs of polygons as well. But I've been thinking of that, but it's not so easy. I don't know. Sorry. That was a quick answer.
Question was longer. Yeah, so we resume at 2:40, but let's thank